Hi, this is Harsh from Indian Institute of Technology, Hyderabad, and the title of our work is Improving Adaptive Bayesian Optimization with Spectral Mixture Kernel. First, we'll present a quick overview of the paper, its main results, and dive into the specifics after that. Suppose we want to find the optima for a black box function, and we don't have an analytical expression for the function, nor its derivatives, and the function is expensive to evaluate. In such a situation, Bayesian optimization is a gradient-free, global optimization approach to find the optima with the minimum number of objective function evaluations. In Bayesian optimization, a surrogate model incorporates prior belief about the function, and this belief gets updated with each evaluation of the objective. At any given iteration, an acquisition function determines the point of evaluation, either a point where it believes the optima is located or a point where exploration is required. Now suppose we want to find and track the location with the lowest temperature in a building, where this location and temperature changes as we perform an optimization to locate it. Or we want to optimize a machine learning model hyperparameters to best fit on a temporally evolving dataset. In such cases, adaptive Bayesian optimization extends the framework of Bayesian optimization to dynamic problems where the objective function value changes with time. Now in adaptive Bayesian optimization, as the Gaussian process has been trained only on past data, we can predict well only a fixed distance away in the time dimension. This is the feasible region of prediction beyond which the Gaussian process has high uncertainty in its belief about the objective function. In the current form of adaptive Bayesian optimization, the squared exponential kernel is being used, and it can be seen from the equation of this kernel that as we move farther away in time, the value of the kernel goes to 0 exponentially. Due to this, the predictive mean goes to the mean of the Gaussian process prior. This limits the feasible region of future prediction to a small value, affecting the predictive capability of the model. We propose to overcome this by using a richer class of kernels called spectral mixture kernel. The spectral mixture kernels are stationary kernels that model the spectral density as a Gaussian mixture. The general equation of the spectral mixture kernel is shown. With simple Gaussian process regression, we have compared the performance of the spectral mixture kernel with other commonly used kernels like Mattern, squared exponential, rational quadratic, and periodic. It is easy to see from this graph that the spectral mixture kernel performs exceptionally well for extrapolation tasks. This is our proposed kernel for improving adaptive Bayesian optimization. The kernel is a product composition of the squared exponential in the parameter domain and the spectral mixture in the time domain. The length scale along the time dimension has been taken as the weighted arithmetic mean of component length scales of the spectral mixture kernel. To show the effectiveness of our proposed composite kernel, we performed spatiotemporal minimization on both synthetic as well as real-world data. In all cases, a zero mean GP was the surrogate model and GP LCB was used as the acquisition function. The evaluation metric used was the offline performance, in which lower value is better in our case of minimization. These are the results on synthetic data. The results shown are an average of 10 independent runs. In all cases, we could reach significantly better minima shown by the lower values of offline metric. In most cases, the total number of evaluations were also decreased, showing that our approach could predict farther into the future. This is helpful when the objective function is expensive to evaluate. We did a similar experiment on the real-world dataset of click-through rate data by dividing it into hourly arriving datasets and predicting optimal hyperparameters of a machine learning model to get the best fit on the current data. Again, our approach significantly outperformed the earlier one. This was a quick overview. We'll get into the specifics now. See that at any given time t, the length scale of the squared exponential kernel is Lt. From the pseudocode of adaptive Bayesian optimization, we can see that the feasible set of prediction is determined by this length scale Lt. As the equation shows, the squared exponential kernel can be seen as a Gaussian centered at the previous time of evaluation. So as we move away from the last time of prediction, the value of this kernel goes to 0 exponentially. One approach to increase the feasible region of prediction could be to increase the length scale. But increasing length scale smoothens the function, making it incapable of capturing frequent fluctuations in the objective function. This is why spectral mixture kernel is a better approach, as it can extrapolate farther without losing its predictive capability. Here we explain how the spectral mixture kernel is related to the squared exponential kernel. For stationary and vanishing kernels, the spectral density and the kernel are Fourier duals of each other. If we take the Fourier transform of the squared exponential kernel, we get that the spectral density of the squared exponential kernel is a single Gaussian centered at 0. This suggests that a richer class of kernels can be created by modeling the spectral density as a linear mixture of Gaussians with non-zero means. This gives the spectral mixture kernel, and we have shown its general form here. The resultant length scale of the spectral mixture kernel has been taken to be a weighed linear mixture of the component length scales of each Gaussian. We will now analyze the results on synthetic datasets to see why exactly the spectral mixture kernel works better. For each function, we fixed time variable as the last dimension and treated the other dimensions as the spatial dimensions. We have first visualized the evaluations for adaptive Bayesian optimization on the Rastrigan function. Training points are in yellow, evaluation points in red. We can see that after certain time, the uncertainty is extremely high for the squared exponential kernel, due to which it predicts only corner points in a bid to reduce uncertainty. But the spectral mixture kernel predicts better minima, and it requires very few exploration points to be confident. Even in the cases where our approach required more evaluations, we see that it leads to a significant gain in offline performance. In these cases, the function exhibits more complex temporal changes and needs closer temporal evaluations to keep track of the optima. Therefore, this experiment shows that our approach provides a better balance between finding the best optima and minimizing the number of evaluations. We will now explain our experiment on the real-world dataset. Optimizing click-through rate is a well-studied problem in the internet advertising industry. The ads are required to change dynamically to adapt to temporal changes like recency and seasonality. Thus, the hyperparameters of any machine learning model need to be continuously updated as the data evolves through time to get the best results. We split 10 days of click-through rate data into hourly datasets ordered chronologically in time. For any model M, its objective is to predict whether the ad will be clicked or not based on its attributes. For adaptive Bayesian optimization, its objective is to predict the best hyperparameters of the model M at time t that will best fit the unseen data dt. We use three models: Gaussian naive Bayes, decision trees, and SVMs. The hyperparameters we predicted were prior class probabilities for Gaussian naive Bayes, depth for decision trees, and regularization constant for SVMs. The optimal model hyperparameters predicted by adaptive Bayesian optimization are shown, with the training data in yellow, evaluation points of squared exponential kernel in blue, and those of our proposed composite kernel in red. See that our approach was able to adapt well to the temporal changes in data. The squared exponential kernel, on the other hand, predicts only corner points, as it chooses exploration over exploitation due to high uncertainty. The spectral mixture kernel, when used along with adaptive Bayesian optimization, allows us the flexibility to predict minima that lie farther in the future. We suggest further experimenting with various machine learning models and temporally evolving datasets in order to exploit the usefulness of the spectral mixture kernel. Thank you.